So, the chip scanner has a few applications that I wish to share with you now. The first being the Semiconductor Reverse Engineering. In reverse engineering, an unknown chip is deprocessed layer by layer, and each layer is imaged. So here we have 9 metal layers and the silicon poly layer of an integrated circuit. And the first 3 layers can be imaged with the optical microscope because they have very low resolution structures. But as soon as you want to look at this specific area of the IC, you need electron microscopy to resolve the structures. And so the chip scanner is used to image large areas of each of these metal layers, metal layer 6, metal layer 5, all the way down to metal layer 1, and the highest resolution is silicon poly. The vertical and horizontal stitching of these layers, the 3D stitching of these layers, has 1 to 2 pixel accuracy over each layer, and each layer has a total of 10 to the 10 pixels. So our client here is able to use the accurate large area imaging with 3D stitching that the chip scanner provides in order to successfully reverse technologies down to the 22 nanometer node. Let's have a look at how the chip scanner captures a large matrix of high resolution images. So here we have a 50 micron field of view with all the corrections, and all of these corrections are applied in real time as the image is captured. These corrections are stored in the scanning electronics hardware, and so whenever we scan an image, all of those corrections are being applied in real time. Next, the laser interferometer moves the sample and an image is captured. And then it moves the sample and an image is captured, and this is just repeated over long time periods to cover large areas of this particular layer. So now we have about 250 by 250 microns of image captured. Let's have a closer look. You can see the green annotations are showing the stitching boundaries between the images, and this is a 10 micron scale bar down here, so you can see very excellent stitching already. You cannot detect any errors in the stitching. Having a closer look, let's take a look at this section over here, and we remove the green annotations, and here you can see actually a stitching boundary. But the stitching boundary is not some error in X or Y. This stitching boundary is actually a variation in signal intensity, which is another dimension of stitching errors that I'll come back to a little bit later. But here you can see really X and Y stitching is almost perfect. Let's have a closer look at this section here. And what we see here is 10 nanometer stitching error. This is a 300 nanometer scale bar here. So we see these images can be stitched together down to 10 nanometers. Furthermore, each of the images are captured at very high resolution. You can really see very high resolution structures here on this layer. The blue annotations are currently showing a 1 micron overlap, but this is far more overlap than what is necessary. We only show this overlap to insinuate, to show that stitching errors is far less than 1 micron. So by reducing these overlaps, speed can be improved for capturing these images over large areas. We had a look at the 2D stitching in the last slide. Now I want to have a look at the 3D stitching. Our partners at Micronet Solutions have created this video using their chip scanner instruments as well as their PIX-to-net reverse engineering software to create this video to show the inherent 3D stitching accuracy that is possible with the chip scanner. So, the following video is going to show the images from 3 different layers of integrated circuit, metal layer 2, metal layer 1, and then a poly layer. So first, we see that the PIX2net software can read in the images from the chip scanner in real time. This allows the user to occasionally monitor the chip scanner's imaging progress. Furthermore, the PIX2net software is also capable of aligning different layers of scanning electron microscope images. This is a very large area image that stitched together, one layer being overlaid and aligned on top of the other. So here we are panning around metal layer 2, and this is a 50 and now a 20 micron scale bar. There are no stitching errors observable in metal layer 2. And so we're going to slowly zoom in now. We're looking at the poly layer. This shows the high resolution imaging capabilities. And finally, we have metal layer 2 and metal layer 1 being overlaid at a higher resolution, one on top of the other. The diameter of these vias is 150 nanometers. Now watch what happens when we remove metal layer 2, which contains these vias. You see metal layer 1, we removed metal layer 1, and now we see metal layer 2, and we see that the vias from metal layer 1 has disappeared, and what we have remaining is the shadows on metal layer 2. And this really illustrates very excellent alignment, clearly below 100 nanometer 3D stitching capability that is possible with the chip scanner instrument. So now we are showing different views and excellent 3D stitching on different views of poly and metal layer 1, metal layer 2. So here's just the poly layer, very high resolution structures. Okay. Now the PIX2net reverse engineering software, it can go further and analyze these images and start converting them into CAD. So now we have CAD design file essentially has been extracted from these SEM images, and color-coded features are appearing in CAD for all 3 layers. So this CAD design file can be further analyzed to identify unknown circuitry. And so here the software has identified the Logic 1 library. And we can see that this Logic 1 library actually consists of a few different NOR, NAND, and buffer circuits. Finally, the software can go and extract schematic net lists and schematic diagrams out of these by analyzing the GDS CAD file. And so ultimately we have really a complete reverse engineering workflow, ultimately producing the net list and even the electrical functional models of integrated circuit. So, okay, next, for this reverse engineering software to be able to properly analyze the images need to be of good quality. And therefore, the chip scanner has a variety of primary electron beam landing energies and also electron detectors. So here we see aluminum traces on a silicon background. And in fact, these detectors and energies are having a hard time showing a high contrast that is required for the software to properly work. But if we switch now to the post-lens angular selective backscatter electron detector, we see that these aluminum lines are appearing with very high contrast over the silicon background. And so it's very important to have a variety of electron detectors and primary landing energies. And as for any traditional scanning electron microscope, the chip scanner does have all of these detectors and primary beam landing energies. Okay. And that point is driven home again by this schematic showing the three different detectors that can be used in the chip scanner.